Transformer vector group YD1 or YD11 or YY0 or YY6. Drawing, confirmation and remembering. In this video, we are going to see transformer vector group is YD1 or YD11 or YY0 or YY6 like that. Transformer HV windings are connected with the various vector group as per system requirement or applications like load or synchronized with the grid. If you say, if you see the wall clock, 12, 1, 2, 3 are written it. 12 means 12 o'clock, 1 means 1 o'clock, 2 means 2 o'clock like that. Angle between each is 30 degree. 12 o'clock is considered as reference. If you say 2 o'clock, this angle between 12 and 2 is 60 degree lagging. If you say 11 o'clock, the angle between 12 and 11 is 30 degree leading. In the transformer, HV phase to neutral voltage is considered as reference, that is 12 o'clock. Angle between HV phase to neutral voltage and LV phase to neutral voltage may be 0 degree, 30 degree, 60 degree like that. This is called vector shift. Instead of telling angle between HV and LV by angle, we are using clock position like 12 o'clock, 1 o'clock, 2 o'clock like that. If LV phase to neutral voltage is lagging by 90 degree with the reference to HV phase to neutral voltage, we say 3 o'clock, that is vector shift by 3 o'clock, that is YD3. In the transformer, LV side lagging angle with reference to HV side can be achieved by connecting HV and LV supply terminal and HV and LV terminals, winding terminal in different ways. We are going to analyze now. Basic rating of transformer, voltage level, vector group percentage. You see in this diagram one transformer is there. For this transformer ratings, voltage level, vector group percentage are given. 50 MA is a rating, 220 kV or 110 kV is the voltage level, YD11 is the vector group, 12%. That is, it is consists of 3 individual transformers. So each transformer's rating is 50 MA by 3. So 3 into 50 MA by 3 is the total rating. HV phase to neutral voltage equal to 220 kV by root 3. LV phase to neutral voltage equal to 110 kV by root 3. HV side is Y, LV side is delta. Percentage equal to short circuit impedance divided by full load impedance into 100. That is 201 into 100 divided by 1676. That is full load impedance is 1676. Short circuit impedance is 12% of that one is 201. So 201 into 100 divided by 1676 equal to 12%. Percentage equal to full load current by short circuit current into 100. That is short circuit current equal to full load current divided by percentage 100 divided by 100. That is 1093.4 ampere. Percentage equal to voltage at full load current with the short circuit divided by rated voltage into 100. HV phase to neutral voltage at full load current with the short circuit. Short circuit is in the LV side equal to 15242 volt. Transformer is connected between HV side and the LV side. It is represented in figure 1. Figure 2 is the same one only, but it is called engineering drawing. Capital letter A1 and A2 are R phase HV winding. Capital letter B1 and B2 are Y phase HV winding. Capital letter C1 and C2 are B phase HV winding. Small letter A1, A2 is R phase LV winding. Small letter B1 and B2 is Y phase LV winding. Small letter C1 and C2 is B phase LV winding. Now A1 and B2 of LV side terminal connected. B1 and C2 are connected. Small letter C1 and A2 are connected. This connection is called delta connection. LV side is delta connection. In HV side, A2, B2, C2 are shorted, connected to the neutral. A1, capital letter A1, B1, C1 is connected to the supply side. So this is called YD connection. Capital letter A1 and A2 are R phase HV winding. Small letter A1, A2 is R phase LV winding. Now IR current in HV winding is passing to the transformer. As per Lenz's law, if primary current from A1 to A2, then secondary current flows from A2 to A1. LV side A2 to A1 it is passing. That is inside the secondary winding, current flows from A2 to A1. If R phase current flows from capital A1 to A2, then secondary current flows from small letter A2 to A1. That is, inside the secondary winding, current flows from A2 to A1. If Y phase current flows from B1 to B2, then secondary current flows from small letter B2 to B1. That is, inside the secondary winding, current flows from B2 to B1. If C phase current flows from C1 to C2, then secondary current flows from C2 to C1. That is inside the secondary winding, current flows C2 to C1. Current flows in primary winding and current flows in secondary winding are represented by vectors. Primary winding current and secondary winding current are in phase with each other. That is inside the winding. Primary winding current and secondary winding current are in phases. R phase current and R phase LV current are in phase. LV side A1 and B2 are shorted. Inside the Y phase secondary winding, current flows from B2 to B1. This current comes from A1 terminal. That is, Y phase winding current, and this IY is coming from A1 and B2. Inside the Y phase secondary winding, Y phase current flows from B2 to B1. This current comes from A1 terminal. That is, at terminal A1, IR current is coming in, IY current is coming out. It is represented by the vector. At terminal A1, IR current, that is R phase winding current, is coming in. IY current, Y phase winding current, is coming out from terminal A1. So the resultant current IR minus IY is coming out from A1 terminal. That is, to the load, IR minus IY current is flowing. In fact, that is, R phase output current from transformer equal to IR minus IY. Inside the B phase secondary winding, B phase current flows from C2 to C1. This current comes from B1 terminal. That is, at terminal B1, IO is coming in, IB current is coming out, going to terminal C2. Inside R phase secondary winding, R phase current flows from A2 to A1. This current comes from C1. That is, at terminal C1, IB current is coming in and IR current is coming out and going to terminal A1, A2. So, R phase output current from transformer is equal to IR minus IY. Y phase output current from transformer equal to IY minus IB. B phase output current from transformer equal to IB minus IR. R phase input current to the transformer is capital IR. Y phase current input current to the transformer equal to IY. B phase current to the transformer IB. You see this diagram, vector diagram. IR, IY, IB is HV side current. IR minus IY minus IB minus IR. This is LV side current. This IR minus IY is leading IR by 30 degree. LV current is leading HV current by 30 degree. So it is YD11. Equal load Z is connected to LV side of the transformer. One side of the load is connected to transformer LV side terminal A1, B1, C1. Another side is connected as star connection at P. P is the virtual neutral of delta side voltage. So VRP, VYP, VBP is each phase voltage of LV side. HV side input current and LV side output current are shown in figure 1. It is represented in vectors. LV side is leading by 30 degree with reference to HV side current. So transformer vector group is called as YD11. LV current flows through impedance, that is load impedance. All three phase voltages of HV and LV side is shown in figure 2. LV side phase to virtual neutral voltage is leading HV side phase to neutral voltage by 30 degree. So it is called YD11. HV side phase to neutral voltage and LV side phase to phase voltage, that is delta voltage, is shown in figure 3. That is VRN in phase with the VRP. Finding vector group del Y transformer. Here R, Y, B are connected to the source. Source voltages are coming to the transformer. Capital A1 and A2 are delta side terminal. They are HV side voltage terminals. Small letter A2, A1 are LV side voltage terminals. So the winding terminals. If primary current flows from A1 to A2, then secondary current flows from small letter A2 to A1. That is, inside the secondary winding, current flows from A2 to A1. If R phase current flows from A1 to A2, then secondary current flows from small letter A2 to A1. That is, inside the secondary winding, current flows from A2 to A1. If Y phase current flows from capital letter B1 to B2, then secondary current flows from B2 to B1. That is, inside the secondary winding, current flows from B2 to B1. Inside the R phase primary winding, R phase primary current flows from capital A1 to A2. This current comes from V2 terminal. That is, at terminal A1, IY is coming in, IR current is coming out. So, IY minus IR current is going to R phase supply terminal. That is, from R phase supply terminal, IR minus IY current is coming out and going to terminal A1. Transformer R phase input current, HV current is equal to IR minus IY. Transformer Y phase input current, HV current equal to IY minus IB. Transformer B phase input current, HV current equal to IB minus IR. Transformer R phase output current, LV current equal to IR. Transformer Y phase output current, LV current equal to I small y. Transformer B phase output current, LV current, I small b. See in the figure A, IR, IY, IB, that is small letters, are as LV current. Capital IR minus IY, R phase HV current. capital IY minus IB, Y phase current, capital IB minus IR, blue phase current. This HV current is leading LV current by 30 degree. If we consider LV current as reference. But as per our rule, dy, the HV side is delta. That is IR minus IY is HV side. So if you take IR minus IY as reference, this LV current is lagging by 30 degree. That is, it is shown in figure B. So it is called as dy1. YD11, dy1 connections are same except HV and LV voltages. Finding vector group YD. See the diagram. HV side is star, LV side is delta. From the diagram itself, you can say the current flow. R phase output current from transformer equal to I small r minus I small v. Y phase output current from transformer equal to I small y minus IR. V phase output current from transformer equal to IB minus IY. R phase input current to the transformer equal to I capital R. Y phase input current to the transformer equal to IY. V phase input current to the transformer equal to IB. You see the diagram. IR, IY, IB is the HV current. The IR is considered as a reference. IR minus IB, IY minus IR, IB minus IR is LV current. This LV current is lagging the HV current by 30 degree. LV current is lagging the HV current by 30 degree means it is YD1. Finding vector group dy. See the diagram. HV side is delta, LV side is star. Now you can say the current flow. R phase input current to the transformer IR minus IB. Y phase input current to the transformer I capital Y minus I capital R. B phase input current to the transformer is equal to I capital B minus I capital Y. R phase output current from the transformer is equal to I small r. Y phase output current from the transformer is equal to I small y. B phase output current from transformer is equal to I small b. We see the vector diagram. IR minus IB, IY minus IR, IB minus IY is a HV current. I small r, I small y, I small b is the LV current. Now LV current is leading HV current by 30 degree. So it is called dy11. YD1 and dy11 connections are same except HV and LV. Phase rotation. If we consider transformer, R phase, Y phase, B phase are output. These are connected to R phase, Y phase, B phase of terminals. If the Y phase is connected to R phase terminal, this called phase rotation. That is, Y phase connected to R phase terminal, B phase connected to Y phase, R phase connected to B phase. This is called phase rotation. If you see the sequence, it is a right sequence only, positive sequence only. So here consider here diagram YY0. This Y phase is connected to R phase terminal, Y phase like that. So this is considered as a YY4. You see that another configuration. Output of B phase is connected to R phase. Output of R phase is connected to Y phase terminal. Y phase of the Y phase output is connected to B phase terminal. This is called YY8. This is called phase rotation. Vector shift 12 o'clock, 1 o'clock, 2 o'clock up to 11 o'clock. You see this table. Left side YY, YY, YD, YD is written. In the top, normal and phase rotation is written here. If we take YY as normal, it is YY0. It is if any phase rotation is happened, then it is YY4 or YY8. Then second YY. This is one Y connection is reversed. That is, instead of A1 A2, it is A2 A1. Then it is reversed. So Y normal is YY6. Any phase rotation is happen, then it is YY10 or YY2. Now YD normal. If the connection is YD and normal, it is YD11. That is IR minus IY. If its phase rotation is happened, then it is YD3 or YD7. Another is YD1. YD1 is IR minus IB, normal. If a phase rotation is happened, YD5 or YD9. A. Procedure to confirm the vector group from drawing or design. In the drawing or design, number one, if YY, then it is 12 o'clock or 6 o'clock. 6 is reversal of 12 o'clock. And normal or phase rotation, then conclude from 12 o'clock, 4 o'clock, 8 o'clock, 6 o'clock, 10 o'clock, or 2 o'clock. If YD, then it is 11 o'clock, that is IR minus IY, or 1 o'clock IR minus IB and normal or phase rotation. Then conclude from 11 o'clock, 3 o'clock, 7 o'clock, 1 o'clock, 5 o'clock, 9 o'clock. If dy, then consider LV as reference and conclude from 11 o'clock, 3 o'clock, 7 o'clock, 1 o'clock, 5 o'clock, 9 o'clock. If it is YD11 or YD3 or YD7, then it will be dy1 or dy5 or dy9. If it is YD1 or YD5 or YD9, then it will be dy11 or dy3 or dy7. B. Procedure to make drawing or design from data. In the data, number one, if it is 12 o'clock or 4 o'clock, 8 o'clock, 6 o'clock, 10 o'clock, or 2 o'clock, then it is YY or YY reverse and normal or phase rotation. Draw the diagram. If it is 11 o'clock, 3 o'clock, 7 o'clock, 1 o'clock, 5 o'clock, 9 o'clock, then it is YD IR minus IY or YD IR minus IB and normal phase rotation. Draw the diagram. If it is dy1 or dy5 or dy9, then draw the diagram for YD11 or YD3 or YD7 and do mirror image of it, verify it. If it is dy1 or dy3 or dy7, then draw the diagram for YD1 or YD5 or YD9 and do the mirror image of it, verify it. From this video, you understand about transformer vector group YD1, YD11, YY0, YY6 like that. In the drawing, you can easily confirm the transformer vector group. Thank you very much for watching this video. If you need any clarification, you send mail to us. Our email ID is anbu.electric.y@gmail.com.